In this video, we'll look at some examples to show how we can use Green's theorem to help us calculate line integrals of the form f dot dr over simple closed curves. Remember that Green's theorem states the following. Let C be a piecewise smooth simple closed curve with positive orientation, and let R be the region enclosed by C. If f is the vector field with components m and n, then the line integral of f dot dr over the curve C is the double integral of partial derivative of n with respect to x minus the partial derivative of m with respect to y over the region R. So let's consider the following example. In this example, we have the vector field f with components sine y and x cosine y. And let C be the rectangle starting at the origin, going to 2, 0, then to 2, 3, then to 0, 3, and then back to 0, 0. We want to find the line integral of f dot dr over the closed curve C. Start by drawing a picture. We have the rectangle starting at the origin, going to 2, 0, then going up to 2, 3, over back to 0, 3, and then back to the origin. So we want to calculate the line integral over C of f dot dr. Now normally if we want to calculate this line integral, we would need to break up the curve into 4 pieces, each of the 4 line segments, and that could be a lot of work. But with Green's theorem, we can do all of this with a double integral. So the line integral of f dot dr is equal to the double integral over our region R of the partial derivative of n with respect to x minus the partial derivative of m with respect to y dA. In our problem here, m is sine y and n is x cosine y. And our region R is the region inside this rectangle. For our double integral, let's integrate in the order dy dx. So my first limit of integration would be from 0 to 3, and then my second limit of integration would be from 0 to 2. Now, partial derivative of n with respect to x would be cosine of y, and I subtract the partial derivative of m with respect to y. That's going to be cosine of y again, dy dx. And so this is just the integral from 0 to 3, from 0 to 2 of 0 dy dx, and that gives us 0. Now this answer should make sense to us because here the partial derivative of n with respect to x is the same as the partial derivative of m with respect to y, which tells me that f is conservative. And for conservative vector fields, the line integral over a closed curve is always 0. Let's consider this next example. So we're asked to calculate the line integral of 3y plus x sine x dx plus 5x minus e to the y squared plus 1 dy, where C is the circle with radius 5 centered at 3, 4, starting at the origin and going counterclockwise. Let's start by drawing a quick picture. We have a circle centered at 3, 4 with radius 5. So maybe something that looks like this, going counterclockwise. So while this line integral isn't written in the form f dot dr, we can think of it that way by taking f to be the vector field with x component 3y plus x sine x and y component 5x minus e to the y squared plus 1. So here m is 3y plus x sine x and n is 5x minus e to the y squared plus 1. According to Green's theorem, the line integral of m dx plus n dy is the double integral over the region R of partial derivative of n with respect to x minus the partial derivative of m with respect to y dA, where R is the region inside the circle. So here we have the double integral over the region R of the partial derivative of n with respect to x. Since n is 5x minus e to the y squared plus 1, this partial derivative is just 5. Then I have minus partial derivative of m with respect to y. M is 3y plus x sine x, so the partial derivative is just 3 dA. So I'm looking at the double integral over the region R of 2 dA. If I factor the 2 out, this becomes 2 times the double integral over the region R of 1 dA. Now if you recall, whenever I have the double integral of 1 dA over a region R, that's just the area of the region R. So this is 2 times the area of R. Well, R is the circle with radius 5, so its area is pi times 5 squared. So this simplifies to 50 pi. Let's look at a couple more examples. In this example, we're asked to calculate the line integral of x squared y dx minus xy squared dy over the curve C, where C is the triangle starting at the point 0, 0, going to 2, 4, then to 0, 4, then back to the origin. As always, I'll start by drawing a picture of this curve. So I have the curve starting at 0, 0, going up to 2, 4, going over to 0, 4, and then back to the origin. Again, Green's theorem tells me that the line integral of m dx plus n dy is the double integral over the region R enclosed by our curve of partial derivative of n with respect to x minus partial derivative of m with respect to y dA. So in our case, m is x squared y and n is negative xy squared. Now here, my region is this triangular region. And when I'm doing the double integral, I have a choice of doing this with respect to y first, then x, or x first, then y. Let's choose to do this with respect to y first. So my bounds for my y, the lower bound, would be the line y equals 2x, and the upper bound is y equals 4. And in this triangular region, my x's go from 0 to 2. So we have the double integral of the partial derivative of n with respect to x. N is negative xy squared, so its partial derivative with respect to x is minus y squared, minus the partial derivative of m with respect to y. M is x squared y, so my partial derivative gives me x squared here. And again, I'm doing my double integral in the order dy dx, where my limits for the y are 2x to 4, and my limits for the x are 0 to 2. I won't go through the details of this calculation, but you should end up with negative 104 over 3. I want to mention that doing the line integral without Green's theorem would be much more tedious. You would need to break apart the triangle into 3 different segments, find parameterizations for each of those segments, and then evaluate the line integral on each segment. So Green's theorem is a really useful tool in helping us compute the line integral. Let's look at one last example. Here we have the vector field f with components x cubed minus 2xy and x squared plus y squared. We're asked to find the line integral of f dot dr over a curve C, where C starts at 3, 0, follows the arc of the circle with radius 3 centered at the origin to the point 0, 3, then goes to 0, 0, then back to 3, 0. Let's start by drawing a picture. We start at 3, 0, and then we're following the arc of a circle to 0, 3. Then we go down to 0, 0, and then back over to 3, 0. So Green's theorem tells me that the line integral of f dot dr over the closed curve C is equal to the double integral over the region R of partial of n with respect to x minus partial of m with respect to y dA. This time R looks like a polar region, so I'm going to do this double integral using polar coordinates. So I have the double integral. Partial of n with respect to x gives me 2x minus the partial derivative of m with respect to y, that gives me minus 2x, and then dA. Since we're doing this in polar coordinates, I'm going to replace the dA with r dr d theta. Now for this region, I'm within a circle of radius 3, so my r goes from 0 to 3. For my theta, I'm looking at a quarter of a circle in the first quadrant, so my thetas go from 0 to pi over 2. So this is the integral from 0 to pi over 2, integral from 0 to 3, Within the integral, I have 4x, but I need to write this in terms of polar coordinates. So I have 4r cosine theta times r dr d theta. So this is the integral from 0 to pi over 2, integral from 0 to 3 of 4r squared cosine theta dr d theta. I won't go through the details of this calculation, but you should end up with 36. So that's it for this video. Thanks for watching.